Jai Hind everyone, my name is Mukulit Goel and I am Assistant Professor in Department of MCA. And today I am discuss our topic from the subject Computer Organization and Architecture, subject code 105 on the hardwired and the microprogram control. So the content of my slide is bus organization of CPU, hardwired control unit, microprogram control unit, micro instructions, field descriptions, micro instruction format, and some of the numerical examples which are very important for the prospects of understanding the microprogram control and also for the examination purpose of students. So I will start with the bus organization of CPU. So it is the bus organization of CPU in which what we have seen is the processor bus, ALU, registers, instruction registers, some control signals, program counter, address register and data register which is connected to the memory. So the ALU is working on one problem which came from the processor bus, which is denoted by Y, and have two inputs A and B, and there are some functions which have been executed on them that might be addition, subtraction, AND gate, OR gate, and the output is stored in Z, and that output has been stored in the travel through processor bus, and that processor bus will distribute it into the memory through address register and data register, the program counter, and have some registers. After bus organization, there is a hardwired control. The hardwired control is used to execute the instruction which CPU must generate and have some proper sequence of operation. The hardwired control unit approach views the controller as a sequential logic circuit to finite machine that generates a sequence of control signals in response to the externally supplied instructions. The externally supplied instructions are through instruction registers. That instruction registers have been traveled contains the instruction through some control signals. Okay, so it is a diagram of the hardwired control unit. So the hardwired control unit is normally of 16 bits. Its instruction register is of 16 bits, in which 0 to 11, matlab 11 bits is for control unit. Then 3 units are being used by the 3/8 decoder, and the 1 bit is being used for the travel of instruction. It has the decoder which have 14 into 16 bit decoder, 4-bit sequence counter which have the increment or the instructions which can be increment, clear or something. Then from the control logic gates there are some control outputs, and in control logic gate there are some inputs which have been given to the control logic to the control unit which controls the logic gates, and it will generate some outputs. After that there is a program control unit, microprogram control unit, in which there is some external input that comes into a sequencer. That sequencer generate the next address. Then next address sequencer, say the control goes to the control address register which we call CAR, then to the control memory, and then control data register, and that control data register constitute the control word. Control word basically a 14-bit word which consists the 3 fields of input which we call F1, F2 and F3, and the last 5 bits as of operation. So through this the next iteration information is travel through these this way only. So when the next instruction comes about from the next address, then the next address generator generates a sequence. Then it again goes to the control address register, then control memory, then control data register, and then creates a control word. In the same way, the microprogram control unit of a basic computer works. Then I come to the micro instruction field descriptions. It is a very important part because it is have the 5 functions, which is F1, F2 and F3. So what we want to what I want to explain through this is, it has a 7 functions, and each function have some micro operation. Each function denotes some micro operation. Like if I talk about the F1 functions, the 0, 0, 0 represents none, means there is a no micro operation. Then 1 bit represents addition, which is addition into accumulator, means accumulator plus data register. 10, 0, 1, 0 represents clear accumulator. 0, 1, 1 represent increment accumulator. 100 represents data register to accumulator. DRTAC means data register to accumulator, means whatever the data is in data register, that is transferred to accumulator. Then comes 101, which represent data register to address register. 110 represents accumulator to program counter to accumulator, and 111 represents write operation, means the data which has been in the data register have been write into the accumulator. It is the micro operations or the symbols in the function F1. Now we come to the functions F2, in which same bit representation, which is 00, 001, 010, 011, 100, 101, 110 and 111. But the operations which have been done are different in F2 function, and their representation is also different. So in F2 function, in F2 field description, the function which is executed for by 00 is none. For 001 is subtraction, AC minus data register, means the values are subtracted. While in the field descriptor F1, the function done by the bit 001 is addition. In the same way, 010 represents the OR operation, 011 represents the AND operation, 100 represents the read operation, 101 represents the accumulator to data register, 110 represents increment data register. In F1 field descriptor we increment accumulator, and in F2 field descriptor we increment data register, and 111 represent program counter to data register. Now we come to the another field description, which is F3. In F3, 00 represents the same, which is no operation, but 001 represents the XOR, 010 represents the complement, 011 represents the shift left, 100 represents shift right, 101 represents increment program counter, 110 represents address register to program counter, and 111 represents the reserve word. So these are the micro operations. Different micro operations represented by the different field descriptors which have the same value, but the operations for each field descriptor is different. And now we come to the micro instructions, which is for branching symbols. These binary codes are for branching, in which 00 represents the jump call, 01 represents the call, 10 represents the return, and the 11 represents the mapping. And these are the same in both the symbols. So what is the micro instruction? Basically, micro instruction formats for the control memory, which is the 20 bits of the micro instruction divided into 4 functional parts, in which the 3 fields F1, F2 and F3 specify the micro operations for the computers. The micro operations are subdivided into 3 fields of 3 bits each, means the F1, F2, F3 constitute the 9 bits. The 9 bits, this gives you a total of 21 bits. How? The 9 bits are for F1, F2 and F3. Then 7 distinct micro operations. Okay, so these three fields are give the 21 micro operations for 7 distinct micro operations. Three functions describe 7 different micro operations. So it will constitute a total of 21 micro operations. Then CD field and the BR field, which is these are the BR fields and the CD fields for the branching, specifies the type of branch to be used and specifies the status bit. Then address field contains the branch address and it is up to the 128 bits. So it contains a 2 raised to the power 7 means 7 words. So it is its format. So 3 is for F1, F2, F3. Then 2 for the condition branching, 2 for the branching and 7 for the address field. So 2 raised to the power means 7 bit is used for the address field. So in this way it consumes 9 bits, 11, 13 and then 20 bits. So this micro instruction format consists of the 20 bits. After this micro instruction format, what I will do, I will explain it using a numerical on micro instruction. So in what we have to define कि this micro operation, how will we represent this micro operation, how we represent this micro operation. What is this micro operation is saying that we are adding something, means we are adding AC plus 1 and DR plus 1. So what we are doing in example 1a, we are incrementing the value of accumulator and incrementing the value of data register. So what we have to do, we have to check the values in the field descriptor, all the field descriptors, which is F1, F2 and F3. So for the A part, what we have to check F1, F2 and F3. So when we are going to F1, F2 and F3, what we are seeing that for incrementing an accumulator, we are using the code 011 in F1. So 011 in F1 for A part. This is our 3 bits now. 0, 1, 1. Next is DR plus 1. So we will check in which field we have incrementing the data register. So data register we have incremented in F2 field. So its value is 110. So in F2 we write 110. Okay. And there are only 2 operations. For F3 it is 00. So with this example, what we come to know? We come to know that there only 2 operations are executing, which is incrementing into the accumulator and incrementing into the data register. And whichever field is not using, we write just 00. So the 9-bit address for A part, 9-bit address for A part is 0, 1, 1, 1, 1, 0, 0, 0, 0. In the same way, if we come for the B part, so it is the 9-bit address for A part. Now we come for the B part. In B part, what we are doing, we are incrementing the program counter and transferring the address register into the data register. So incrementing our program counter. So the program counter is incremented using a field in field descriptor F3 and the code is 101. So first we write F1, F2, F3. So here 3 bit, here 3 bit, here 3 bit. So program counter plus 1 is 101. So in F3 we write 101. Now we come to memory register to data register, where it is memory register to data register to memory register in F2, and that is represent using 100. So we write 100 here. And the field A for F1. So field A for F1 is 000. So for B, our 9-bit code is 000, 100 and 101. So I will starting with the B part, in which there is a first is we are incrementing the value of program counter. Then we are transferring the data from memory address register to memory register. So what we have to do, we have to check the values in the all the field descriptors. So program counter is incremented in F3, and the value of memory address register have been transferred to data register in F2, which have the code 100 and it has the code 101. So in this, under the field of F3 we write 101, and under the field of F2 we write 100, and in the field of F1 we write 000, because in this micro operation there is no values from the field 1, there is no operation from the field 1 descriptor. So the 9-bit micro operation for the problem B is 000, 100 and 101. Now we take the part C. In the part C, first we are transferring the AC to data register and data register to AC. So AC to data register and data register to AC. So in this we use F2 and F3, which is 101 and 100. So for part C, 100, 101. So it is 100, 101 for F2, sorry, 101 for F2 and 100 for F1 and 000 for F3. So the 9-bit operation for the part C is 100, 101 and 000. So in this way we create a 9-bit micro operations for the given micro operation, which have the micro operation. Now if suppose these micro operations are not given, you have given with the symbols, like in this example. So in this example what we are having the micro symbols as a read, increment program counter, accumulator to data register to accumulator, and address register to program counter, data register to accumulator, and write. So the same way we have to solve it for F1, for F2, for F3. For F1 we are for problem A, we have to check where we have read in F2, where we have increment program counter, we have increment program counter in F3. So the field is 101 and 100. So 101 and 100. So here we write 100, here we write 101, and here we write 000. So for problem A, 9-bit is 000, 100, 101. Check it. For read we have, for read we have 100, for read we have 100, and for increment. Okay. So if we comes to problem B, then data register to accumulator, Data register to accumulator is 101. And data register to accumulator to data register is 101 in F2, and data register to accumulator is 100 in F1. So 100 in F1, so we write 100, 101, 0, 0, 0. This is the 9-bit field for the B part. Okay. So in this way, we convert this and we create this 9-bit address using the micro operations or using the symbols into the binary, and all these symbols create some control word with the operations of 5 field, which is the 14-bit. These fields create the micro operations of 20 bits. With the address of 7-bit, it comes into the 21-bit with the condition branching and the branch field, bits of condition branching and the branch field. And in this way, I think these numericals are clear to all, and thank you very much.